Good morning. Today we're going to look at another application that's graphical in nature of the first derivative. And in particular, we're going to be looking at finding extreme values for various functions. So when we talk about extreme values, we're referring to points that are peaks in the graph or points that are valleys in a graph. And we call these points maximum and minimum points respectively. So I've just drawn this quick sketch here. Maximum points would be located here at A and C. And of those two maximum points, the absolute maximum is considered to be at A. And that is because it is the highest of the two peaks. The higher of the two peaks. Minimum points in the graph would be located at B and D. And of these two relative minima, the absolute minimum point is said to be at D. So it is the lower of the two minimum points here. Okay, so just trying to get you used to a little bit of the terminology there. Now, here is going to be our key to solution. If you look at all of those extreme points, so all of these maximum points, all of these minimum points, what can be said about the slope of the tangent line at each point? So if we were to draw a line tangent at each point, okay, so I'll just do a little quick sketch here of that. So picture a line that intersects the curve only at point A, only at point B, and so on. So these are the tangent lines that I've just drawn here. You should note that they are all horizontal lines. And therefore, we can say at all extremes, the slope of the tangent line is 0. Okay, so at any extreme point, if you draw a tangent line, it will be horizontal. And so that gives us a method of locating these extreme points for any graph. If the slope of the tangent line is 0, this means that the first derivative is 0. So to locate all extremes, set dy by dx or y prime equal to 0. So take the first derivative, set it equal to 0, and solve in order to determine where the maximum and minimum points lie. Okay. So now we're going to look at a first example. Okay, so here is our first function. Y is equal to 2x cubed minus 9x squared plus 12x minus 3. And if we would like to locate the maximum and minimum point or points, we're going to take y prime and set it equal to 0. So what is y prime here? Well, the derivative of this polynomial is 6x squared minus 18x plus 12. So there's y prime, and it is being set equal to 0. Because again, the slope of the tangent line will be 0 at a maximum point and at a minimum point. Okay, now we're charged with solving this for x. We need to figure out what two x values will make this equal to 0. We suspect two values simply because it is x squared. Okay, so you can do this in different ways. I'm noticing that all of these numbers are divisible by 6, so I can start like this. All right, and now what I have is a trinomial with a leading coefficient of 1. And this kind of trinomial is very easy to factor. So I think I'll use factoring here. Okay. And having said that, if you prefer to use the quadratic formula on your trinomial, you can certainly do that. And you can do that with this form here. You'd have A is 6, B is negative 18, and C is 12. Or you can use this form here. A is 1, B is negative 3, and C is 2. So if you want to use the quadratic formula, you can go ahead and do that. But as I said, since this has a leading coefficient of 1, it's going to be easy to factor. The factors will be of this form. And in order to fill this in, I need two numbers that multiply together to give me positive 2. The same two numbers, when added, should give me negative 3. So we say the product of the numbers should be 2. The sum of the numbers should be negative 3. And so what numbers will satisfy these conditions? The numbers are negative 1 and negative 2. They multiply to give you 2 and add to give you negative 3. So those are the numbers that go in here. Those are not the x value answers. So the x value answers are obtained once you set each of these factors equal to 0. So if x minus 1 is 0, then x is 1. If x minus 2 is 0, then x is 2. So these are the two x value answers that you would get if you use the quadratic formula on either of these equations. Okay, so now we know where we will have our extremes. One at x is 1 and one at x is 2. Now, we should write these as ordered pairs. So that means figuring out the height associated with each of these x values. So we take 1 and substitute it, and we take 2 and substitute it to get those corresponding y values. So when x is 1, then y will be 2 times 1 cubed minus 9 times 1 squared plus 12 times 1 minus 3. Okay, so what is that? That's 2 minus 9 plus 12 minus 3, and that'll give you 2. Okay, so now we have the ordered pair 1, 2. Okay, and we'll do the same thing. We will also substitute x is 2. So then y is 2 times 2 cubed minus 9 times 2 squared plus 12 times 2 minus 3. So that's 16 minus 36 plus 24 minus 3. And if you work that out, you'll get 1. So now we have the ordered pair 2, 1. Okay, so now what do we know? We know that these 2 points are extremes in the graph. We do not yet know for sure if one of them is a minimum point and the other is a maximum point. We can make a pretty good guess if you just think about plotting these points and trying to connect them with a smooth, continuous curve, you can pretty well guess that there will be one maximum and one minimum, and you can also decide which is which. But we have a way of verifying that, and it is called the second derivative test. Okay, so the second derivative test says, take a look at the value of the second derivative. If the second derivative, y double prime, is less than 0, so if the second derivative is negative at the extreme point, then that extreme point is a maximum. While if the second derivative at the extreme point is greater than 0 or positive, then the point is a minimum in the graph. Okay, perhaps I can just explain this quickly by going back to our diagram. To understand this, you have to realize that the second derivative is an expression of how the first derivative is changing. So if the second derivative is negative, it means the first derivative is decreasing. So we're suggesting that at a maximum point, y prime is decreasing. So let's see why that's true. Okay, so remember, this is a maximum point. Is y prime decreasing here? Yes, it is. Remember, y prime is the slope of the tangent line. To the left of point A, the slope of the tangent line would look like this. It would be rising to the right, positive. At A, the slope of the tangent line is 0. To the right of A, the slope of the tangent line will be negative. The line would be falling to the right. So the first derivative was positive, goes through 0, and then is negative. That is definitely a decreasing first derivative, which means that at A, y double prime is less than 0. Okay, and the reverse, of course, will be true. At a minimum point, y double prime is positive because the first derivative is increasing at a minimum point. So here's a minimum point. To the left of it, we have a negative first derivative. Then the first derivative is 0. Finally, it is positive to the right. So the first derivative is increasing from a negative number through 0 to a positive number. And an increasing first derivative corresponds to a positive second derivative. Okay, so that's just an explanation of this, but it is suffice for you to remember the actual rule. So going back to our example, we have a curve with two extremes. Let's identify which extreme is the maximum and which is the minimum by performing the second derivative test. So first, we need to know what is the second derivative. Well, this is the first derivative here, 6x squared minus 18x plus 12. So its derivative, therefore, is 12x minus 18. So that's the second derivative. So now what we have to do is evaluate it at the two extremes. So we're going to evaluate it at the points we found here at 1, 2, and 2, 1. At the point 1, 2, the second derivative is 12 times 1 minus 18, which is negative 6. So this is a value that's less than 0. What does it mean when the second derivative is less than 0? It means you have found a maximum point. So this point right here is a maximum. Now, what about at the point 2, 1? At the point 2, 1, so we substitute x equals 2, we get 12 times 2 minus 18, and that's positive 6. The fact that that number is greater than 0 means that the extreme point here is actually a minimum. So now we're finished, and our conclusion is there is one maximum at the point 1, 2, and one minimum at the point 2, 1. Okay, so we've got all our calculus done. We're sure about our findings, and now I want to show you the graph that corresponds to this example. Okay, so we are going to look at the top graph here together. Okay, so this is a graph of y equals 2x cubed minus 9x squared plus 12x minus 3. It's the example we just completed together. Take a look at this graph for a moment. It's smooth and continuous. It means that this end of the graph would continue down in this direction and here up in this direction. And what we have is at the point 1, 2, which I'm going to put a little dot, is right there in the graph. We do indeed have a maximum. And at the point 2, 1, which is right here in the graph, we do indeed have our minimum. So two extremes, just like we predicted with our calculus. Okay, so what I'd like to do now is a second example. And once again, we're going to go through the same process. So we will be taking the first derivative and setting it equal to 0 to find the extreme points. And following that, we will also perform the second derivative test. So let's go ahead now and try that example together. Okay, so here we go. At the top of the page, we have y equals 3x to the 4 minus 4x cubed minus 12x squared. So let's go ahead and work this one out. So how do we start? We're going to be taking the first derivative and setting it equal to 0. So the first derivative is 12x cubed minus 12x squared minus 24x, just like this. So we take that now and we set it equal to 0. Okay, now that we do have the right side 0, we notice that there is a factor of 12 present, and so we can simply remove that factor from all the terms. Additionally, there is an x present in all terms. Now this you can't just remove completely. You do have to factor it out. Okay, so you can In other words, common factor 12x if you like this. And that'll leave you with x squared minus x minus 2 in here. Okay, the 12 out front is optional, so you can get rid of the 12 altogether if you like, but the x has to stay here because it's going to provide one of our roots. You see, y prime is of degree 3, so we should actually have 3 results here, 3 answers in our problem. Okay, so this again is a trinomial with a leading coefficient of 1, so it's quite easy to factor. So I'm going to factor that now. So we know that it'll be of this form with an x in the front here for each. And so I need to fill this in with the 2 numbers that can multiply together to give me -2. The same 2 numbers would add to give me the coefficient of x, which in fact is -1. So what numbers here satisfy these conditions? The numbers would be a -2 and a +1. They can multiply to give you -2 and add to give you -1. So these numbers go in here, a -2 and a +1. Okay, like that. If you want to use the quadratic formula on this thing instead, you can, right? Quadratic formula can be used if it's of the form ax squared plus bx plus c. But with the quadratic formula, you'd have a is 1, b is -1, c is -2. Okay, so my 3 answers are obtained by setting each of these factors now equal to 0. So 12 times x is 0, x minus 2 is 0, and x plus 1 is 0, like this. And in doing so, I can solve by, in the first case, dividing both sides by 12. Here, adding 2 to both sides, and here, subtracting 1 from both sides. So we end up with these 3 answers. X is 0, x is 2, and x is -1. So 3 extremes. And as I say, we did expect that because we had y prime of degree 3. Okay, so now what we should do is find the y values that correspond to these x values because we want ordered pairs. So we're going to work out y when x is 0. And we're going to work out y when x is 2. And we're going to work out y when x is -1. Okay, so let's go ahead. When we substitute 0 in here, you should be able to see that y will be 0. Okay, so that's fairly obvious. When you substitute 2, you know you have to do 3 times 2 to the 4 minus 4 times 2 cubed minus 12 times 2 squared, like this. So this is 48 minus 32 minus 48. So you should get -32 here. And when you substitute -1, so it's 3 times -1 to the 4 minus 4 times -1 cubed minus 12 times -1 all squared. This will be 3 And since this is -1, it'll be 3 plus 4 minus 12. And so you will get -5. Okay, I'm going to grab the calculator for one moment here because I want to make sure you realize how to evaluate that. Okay, so when you've got a negative number to substitute, like we do in this case, right, you're gonna be doing 3 times in a bracket, okay, -1 to the power of 4, for example, okay, for this portion here. -4 times -1 to the exponent of 3, or cubed here, okay, minus 12 times -1 in a bracket squared, something like that, okay? The key is the negative numbers must be bracketed in order to evaluate these things correctly. All right, so we're at the exciting part where we can state that we have 3 extremes, and they are the points 0, 0, 2, -32, and -1, -5. So we're at the point where we could state that these 3 values are extremes in the graph. And so what does that mean? It means probably we have 2 mins and 1 max, or 2 maximum points and 1 minimum point. And as I said, you know, you could try to graph this, put the 3 points on the paper, and you probably get a pretty good idea of what you have, because you have to connect them with a smooth curve. This is continuous. It's defined everywhere, right? The domain is all of the real numbers. So once you plot the 3 points and you try to connect them, you'll get a good idea of what you're dealing with. But that's not good enough for us because we are calculus students. So what we're gonna do is use the second derivative test. Okay, so let's do the second derivative test now. So what does that require? It requires us to find, first of all, the second derivative. So y double prime is the derivative of y prime, and therefore it's 36x squared minus 24x minus 24. So 36x squared minus 24x minus 24. And then we have to evaluate the second derivative at the 3 points. So let's evaluate it at 0, 0. Let's evaluate it at 2, -32. And let's also evaluate it at -1, -5. So to evaluate, all we have to do is substitute the x value. So you can see when you put 0 in for x here, what value will you get? You'll get -24. This number is less than 0. So what does that mean? It means the point 0, 0 is a maximum point. Okay, now we substitute x equals 2. So 36 times 2 squared minus 24 times 2 minus 24 equals, okay, so you can work that one out with your calculator. I got 72 when I did that. Okay, and the fact that it's greater than 0 means that this point is a minimum. Okie dokie. Last one. We're substituting -1. So 36 times -1 all squared minus 24 times -1 minus 24. So this is 36 plus 24 minus 24, which means that it is 36. And the fact that this number is greater than 0 means we have found a second minimum point. So we indeed have one maximum point and two minimum points. Okay, now remember that when you have two of the same type, like we did in our original sketch, we were able to state which was the absolute maximum, and it was the higher of the two peaks. And we stated which was the absolute minimum. It was the lower of the two valleys. So this time we have two minimum points. Which one is the absolute minimum? So how do you know which is the lower of those 2 points? The lower graphically? Well, you look at the y value. Which of these would be lower once plotted? This guy right here. Okay, so that means this point is the absolute minimum. So I'm going to write out our exciting conclusion now for this problem. We can say there is a maximum at 0, 0. There is a minimum point. We call it a relative minimum point, and that's at -1, -5. And now I'll say the absolute minimum is at, and that's the point 2, -32. Okay, so this would be our conclusion. There will be a peak at 0, 0, like a hill, right? There'll be a minimum point at -1, -5, and the absolute minimum point will be at 2, -32. Okay, so remember this doesn't mean it's the lowest point in the whole graph. What this means is that of the minimum points that you find, so of the valleys, the lowest valley occurs here. Okay, so I'm going to show you the graph now, and you can see that it agrees completely with the calculus that we did. So let us take a look at the graph together. So can you see that okay? I know I'm still struggling with the whole sunshine coming in, and I've got full blinds on the sliding door here, but it's still an issue, so I'm gonna have to come up with a better solution. All right, in any case, here we go. We're looking at the lower graph now. This is for the example we just completed. Do we have a maximum point at 0, 0? Indeed we do. At 0, 0, we are at the top of that hill. Do we have a relative minimum point at -1, -5? Yes, that's right here in the graph. It's the lowest point of that valley. But there is a lower valley down here. And so at 2, -32, okay, right there in the graph, we have what we call the absolute minimum. And actually, in this picture, it is also the lowest point of the graph. This graph continues up and up here. Okay, so Maybe I'll put a little dot at these actual points. And you can see the graph is in complete agreement with the calculus. So I'd love for you guys to begin practicing these types of questions, okay? So I've put some recommended problems for you in Blackboard. Thanks a lot. Have a great day.